Welcome again to the NPTEL course on storage systems. So far we have been looking at some aspects of ordering. Let me just summarize what all we have done so far, various types of orderings that we looked at. In the beginning we looked at disk ordering, which is done by elevator algorithm. SCSI ordering, these are the protocol level, but it closer to the device level itself, and that uses things like order tag, etc. We next looked at message ordering, such as virtual synchrony, okay, that we just recently looked. We took a reasonably close look at this one. And now you have a few more types of orderings at the file system or kernel level and at the application level. Again, as we discussed before, file system also orders certain things. The way they do it is by synchronous or asynchronous or delayed writes. You can also do ordered writes. I will briefly talk about soft updates later. You also have notions of logging on transactions. Okay. There are various types of ordering that also happens here. There is also one more at the highest level, you might call it application level ordering, and these things are things like fsync, and we look at one model called forder, which one distributed file system called Echo has, which we also discussed briefly last time. So you can see that there is lots of ways in which the IO can get reordered, and therefore the exact semantics is non-trivial. Okay. To work through all these layers is incredibly complicated, and because data is extremely crucial for the functioning of large systems, there is a lot of conservativeness in all these aspects, okay, because something gets wrong, data might be completely corrupted, and if you are unlucky, your kernel data or kernel persistent data, if they get corrupted, then your system is actually gone. Okay, so that's why there is a lot of carefulness with which all this is done. So we looked so far up till message ordering. Now I want to start looking at these aspects. Okay. So one model what I introduced last time was the one distributed file system called Echo. An important thing about this particular model is that it has got a notion of write behind. Again, what's write behind? It is same as write back, except that your write back can take any arbitrary amount of time. Write back takes an arbitrary amount of time, whereas write behind always happens within a fixed amount of time. For example, it can happen if there is something dirty in memory, it will be flushed to disk within a specific period. For example, it could be 30 seconds, 15 seconds or 1 second. Okay. This is what is called file system hardening. In file system hardening, what you try to do is you try to limit the amount of dirty data that can be lost because of a crash in the system. Okay. So basically this particular model uses write behind, and it's a well known technique, but it tries to avoid NFS problems. Okay. And we also looked at some of the high level ideas that this particular system should have. For example, write requested by one client and observed by another, write should be stable. Okay. This across two nodes. On the same node, writes on the same object should be stable in logical order. Okay. And we said that you can have fsync at the application level, and Echo introduces a new model forder, which constrains ordering of write. For example, if I say forder F1, F2, etc., what it means is that any pending operations on F1, F2 are completely performed before you think of proceeding further. So again, this is actually an interesting operation. It doesn't really do anything, it just does ordering, that's all it does. It's similar to if you are used to make files, you have notion of touch. Basically, touch is basically what? It basically changes the timestamp, that's all it does. Okay. Those of you who use make files, you know that there is an important thing called touch. It's similar to this. All it does is it does a null updates on each of them, except it changes the time, that's all. It just basically says that this happened at this part, this is logically happening at this time, that's all it says. So it's purely some kind of a null update, so that you know that some update has taken place, but actually nothing has changed. That's basically what this is. Another thing about this is that it returns immediately, unlike fsync. fsync basically waits for the disk operation to be completed before it returns back. So, f order is basically a way to make sure that certain things are sent to disk in a particular order. Okay. And this is quite important because we are talking about a distributed file system and different parties could be communicating through files, and whether that particular information written through a file makes it to the other side or not is very critical. For example, if I do a lot of writes and I crash, nobody notices it. It's equivalent to a crash, okay, because I wrote something but it never made it to the other side. Nobody saw it. But if I saw it, somebody else saw it, then it better be stable on the side that is sent it, because otherwise it's not equivalent to a crash. Okay. So that's why there is that's why Echo has got this particular model. Again, we briefly went through it last time. We'll just go through it one more time. It has two relations. One is the standard data dependency. It could be within a node and across nodes. Okay. But this one is a partial order for stable writes. The fact that there is a data dependency does not mean I succeed in completely writing it all through to a disk. I might only send a portion of it. Okay. And this is only for stable writes. It's not for other data. Okay. And for this reason, because it's only for stable writes, this is a subset of this. Okay. And just like your Leslie-Lamport's transitive relation across events, this also you can introduce a relation which is transitive, which is closed on either this or this operation. Okay. So basically, Lamport's model was with respect to messages. This is going to be with respect to dependencies, and this one is specifically tailored, this particular one specifically tailored for stable writes. Okay. What is this one saying? O1 arrow O2. This means O2 is dependent on O1, and that means that O1 and O2 should have an operand in common, and O1 is a write. Okay. And O1 has to be done logically before O2, and in case O2 gets done, that means O1 cannot be discarded because it's a write. That means if it has dirtied the buffer cache, that content cannot be discarded. It has to make its way to the disk. Okay. That's what this is. This is basically some kind of guarantee. Again, this particular ecosystem has a small optimization for that reason that it turns out that there is this particular rule, O1 double arrow O2, and this basically is saying that in case O1 arrow O2, and it has to be that O1 and O2 both have to be writes, but not overwrites. Basically, because this particular system, they have decided that this is an interesting optimization possible, which is mostly applicable to most systems, that you don't care about. If you are having overwrites, you don't care which order they go in. Okay. So that's why they decided that it's okay that we don't have to constrain the way overwrites go through. Okay. They can happen in any order. In case you need that constraint also, it's always possible using F order. I can always order it through F order. Okay, if there's a need. Okay. So I'm only saying that O1 double arrow O2 only in case O1 and O2 both are writes. I don't care if it is writes, I don't care. I will not have this particular thing. Okay. Whereas in the data dependency, it may be that that's important. Okay. That's why O1 O2 is this double arrow is subset of the single arrow. Okay. And this one is there precisely because we are talking about stable writes. If O1 has been discarded, it better be that O2 will also be discarded. It's very critical. If O2 does not get discarded, that means again there is some inconsistency in the system. Essentially, somebody has unrolled O1 if that happens, okay, which is not what we wanted. Again, if O1 arrow O2 and O1 O2 are different lengths, because we are a distributed file system, these operations can be on different lines. O1 stable when O2 performed. And basically what does it mean? It means that if O2 has seen something, then it better be that O1 is stable on this node. Otherwise, somebody has seen something and the event that was there on some other node actually disappeared. Okay. Again, this inconsistency. This is also not right. And the reason why this is important is because if you are using normally in regular POSIX kind of machine, oftentimes you use files as a way to transmit information. Now, I want to have the same semantics in a distributed file system. So, it better be that the similar kind of model is present also here, so that I can still write through files and they can communicate through files. What I write in one file, other party is able to see it, and as long as this is guaranteed, that still is the case. And O1 O2 and O2 stable implies O1 stable. Okay, this is the most let us say, it basically says that if O1 has been sent to disk, sorry, O2 is available in disk, O1 also is in disk. Okay, and if fsync of F is successful, F is stable. Okay, so it turns out that each of these things takes care of some particular interesting case, and therefore all these things are required. Okay, to take an example, you have an overwrite F with data 1, again overwrite F with data 2. And as is mentioned, these are overwrites. That means that you are not changing the size of the file. And as per this echoes ordering semantics, this can go in any order. We don't care whether this guy goes to disk first or followed by this. But if it is append, I want to ensure that, suppose I am interested in ensuring that this one happens only after all these things have been sent to disk. So, I have this kind of model. Okay. And so, because there is a dependency between this operation and this operation, there is a dependence, because notice that O1 depends, sorry, O1 arrow O2 if they have some operand in common. So, this operand F is common, therefore, if this is done logically before, then this has to be after. Okay. Similarly, F, these two things also can be done in parallel, because I do not care about overwrites being in the way they go in parallel, the way they, in which order they go. Whereas, if I am interested in making sure this overwrite happens only after these things, okay, only after these things, okay, these two things, okay, then I can ensure there is something called F order, and what this guarantees is that you have to make sure that these are completed before you can get to this one. Okay. Again, this is dependent on your model, the application's models about how things should be flushed to disk. Now, with these things you can essentially implement things like write ahead logging. What's write ahead logging? You append your intentions, means what are the things that you are going to update to log file, and then you say F order log file, let us say it is updating F1, F2, F3, this particular operation, whatever it is doing, whatever file system operation that you are planning to do, it actually updates F1, F2, F3. Then I basically have F order log file F1, F2, F3. That means that the log file should be flushed to disk before I do any of these things, logically. Okay. That is, if this has become stable, that means this also definitely has to be stable. There is no question about, that is what I am asking you to do. Okay. And by putting F1, F2, F3, I mentioned F order essentially doing some kind of a touch operation on these things. Therefore, this operand is early, but modification to F order is earlier than this one, therefore, this has to come before. That is why this is ordered later than this one. Similarly, this operation ordered later than this one, this operation. But notice that there is no connection between these three guys, they can go in any order they like. I am not bothered about which order these three things go. The only thing I am interested in is this one, this has to go before any of these three things. Okay. So, in a sense you can express certain kinds of concurrency that you want in the system, and this F order gives you that handle. Okay. So basically the safe order ensures that none of the updates will reach disk before the log record does. So it has been logged completely, then only it goes. Now something similar is also possible, and actually it turns out in the BSD file system, they have a file system, the 4.4 fast file system. Okay, the later version. There was an earlier version also which did not have this, but the later version post 2000 has something called soft updates. And in this particular file system, all the cache buffers are tracked through the dependency relation in the kernel. Actually, the kernel actually tracks all these things through the buffer cache mechanism. And anytime you flush any of the buffers, you make sure that it's always a consistent cut of the relationship. That is, you never ever do it in such a way that it looks as though, if in case of a crash, it looks as though you've gone back in time. Okay, that is something which they will make sure it doesn't happen. So you group the graph structure in such a way that there is always, in some sense, forward motion. Now this turns out to be complicated also. So I'm not going to go into details, but it turns out because of sharing, there can be some circularities, and these circularities have to be resolved, and essentially the soft update mechanism does some localized undos, so that you still get some kind of a let us say a directed acyclic graph of some kind. Okay. I don't have time to go through it, but it turns out soft updates also does some ordering, but it's done all this is done using the kernel mechanisms of flushing. Okay. So now let's quickly look at other possibilities. Suppose you have the notion of rename. Actually, rename is one of the most complex file system operations. And for example, the definition is here. You have a source and a destination. Okay, and you can see it as, if you look at the description carefully, it has got lots of details. Okay, both must be directories, or both have to be files. They should reside in the same file system. Okay, so there is also some guarantees about crashes. In the system crashes in the middle of the operation, they will either say that you have the old or new. Okay, okay. So they have lots of conditions here, and as we can see here, right, you will find that anytime you do rename, it can touch multiple things. For example, you can, in this case, rename AF and BF, for example, with this thing existing previously. You notice that what are we going to do? I am going to take this particular file and I am going to delete the old file F here in /B, which is a different file, and I am going to take this file and put it into B's directory. Now A's directory has changed because this file has disappeared from its directory. B's directory has changed because a new file has come in, which has got the same name as the previous one, but it's a different file. Okay, that also is gone. Okay, and this file is gone. Sorry, yeah, this file has become this new file, and the old file F has gone. So there are 4 different changes. A has changed, B has changed, this file F has disappeared, and this F has come and sat here. Okay, so modifications. Okay. So the crash can occur any place, anytime. Okay. So if you look at, let's say the file system guarantees some atomicity condition. Let's say the file system already guarantees it. So we are now talking about how to order renames themselves. So there is multiple renames going on. For example, rename /df1 /dfg1, rename /ef1 /ej1. Notice that none of these operands have anything in common, so they can go in parallel. Okay, but this one shares the D directory between these two, therefore they have to be ordered. This one has both D directory and E directory, therefore this one has to be ordered this way. Okay. So what you are guaranteeing is that because all these are ordered through the double arrow relationship, if this has become stable, you are guaranteed this is stable. Similarly, if this is already stable, then all these guys are also stable. Okay. Now, let's consider one important idiom that is widely used: write a file and replace it with another automatically. Why is this so critical? Because all of us use editors. In editing, it is very critical that you are working on a particular file F, you update it. Once the update is completed, you want to replace the old file with the new file atomically. What you are interested in is making sure that whatever happens, I should not lose my updates if possible, and most important, it should not be the case that I lose both the old file and the new updates. Okay, that is a catastrophe. I want to avoid it. Okay, so that is the reason why I need to replace with another atomic. So when I do VI, when I do write and exit, okay, somebody has to do this. When you are using Emacs, somebody has to do this. If you notice in earlier file systems, that is before 1980s, for example, you could lose files. This is one of the things that most people were scared of. But now most file systems take extra trouble because this is the most unpleasant thing that one can imagine. Okay. So this can be done in our system by the following. So I create a file, I add some data to it, I create, because I am going to replace with another thing, right? So basically in the same directory I am going to create a new file, and then, so this was some, you might call it some version of the file. Here what I am doing is, I am not really doing an editing job here, I am just talking about one file that has been created and something has been put into it. Here I create another file, I put some other data into it, and I want to rename it. Basically what I want to make this, whatever is data here should actually be present in /df. Okay. So because of this double arrow relationship, even if some right behind is lost, okay, because if it is lost, what does it mean? It means that I am guaranteeing that if this thing, one of these things died, okay, then I will not get to this point. Okay, that is a guarantee that the double arrow gives me. So even if some right behind is lost, new file replaces old one only if its intended contents are reached disk. The problem with many, let us say, some Unix file systems in the past has been that usually data was not flushed to disk immediately because of write behind or delayed writes or asynchronous writes, but metadata always asynchronous. That means that which are metadata here? This is a metadata operation, this is a metadata operation, this is a metadata operation. In those cases, what will happen is that you do something here, this goes to disk right away, this goes to disk right away, this also can go to disk right away, whereas these two stuff could still be sitting in memory. Okay, and that means that if there is a crash, this /disk F could be pointing to something which was unrelated to what was actually put in. Okay, that is possible. Okay, with these things, it is possible for us to avoid this. With the double arrow, we can always order it right. Okay, here we do not need an F order, but this ordering because of the relationship between these two, we can still ensure that this happens earlier, this becomes stable, then this becomes stable later. Okay. Now, if suppose sometimes you have this notion also, replace a directory with a new version. It is also a common operation. Suppose I have a installation of a particular application, it could be Firefox. You know that Firefox keeps changing, so you have a directory with all kinds of stuff and you want to place it atomically with a new Firefox installation. Okay. We want to make sure that this happens correctly in spite of any crashes. So let us look at exactly the situation here. So make dir /d/new, this is a new directory. So I want to make sure that I can't be keeping on writing arbitrarily into the Firefox directory, because I might write something and I die, or anything can happen. So that way means I don't know what has happened, it becomes good. So what I'll do, I do it in a new directory completely. So I do it in a new directory and I create some file there, append data to it. And then here I am taking, this is the first directory, this is the second directory. Okay. Again I create a new directory. Sorry, I made a mistake. I create a new file and append this. Okay. Now once this is done, I want to rename. I think I made a mistake here. Just a minute. If you look at this one, so there is this operation make dir. You created a new file there. So you created one file f1 here, you created another file f2 here. You put data 1 into this new directory and you created some data d2 into this file f2, and you had an old file and you basically took the directory d and replaced the contents of that d old with d. Now comes this new directory. Now I am interested in renaming this new directory as this particular directory, which also actually has replaced the previous directory. Okay. Now our issue is that if there is a crash, it's possible that data 1 and data 2 they are not on disk, and the only way to do it is by using this f order, which basically makes sure that this and this they get stable, and because this is before this, you are guaranteed that these two things become resident on disk, then only this operation will proceed and let this particular operation proceed. Okay. So normally if you don't have f order, it may be that you will, the D has some junk files in it, because data 1 and data 2 are still not made it to disk, because this path could be quite fast, make dir, create and rename. With f order you are guaranteeing that this happens in the same order. Okay. So the reason why this has happened is because if you notice, there is no connection between D and these operations. Okay. There is no operands are common. Okay. That is why there is no way for the system to order it, even with even if you think that there is a if you take the standard data dependence. Okay. So that's the reason why you will find that these two data may not be resident, and you might actually directly go here, and if there is a crash, then D might be pointing to might have some files which are not the correct data. Okay. So basically what echoes failure semantics is as follows. An application procedure P depends on a write W if P issued write, or if P issued a read write operation O and a W arrow O. Okay. So basically if P has issued, this one is clear, because P issued write, it assumes that it is going to be sitting on disk. That is elementary observation. Okay. Because P issued it, therefore it has to be there. Or if it so happens that P issued some operation O and this word actually depends on W. Okay. That means that since it has issued this, it has been completed somehow. Okay, because this operation could actually be a read also, it could be a read. Okay. That means that P actually depends on write being stable. If it is not there, then there is something essentially again P will have an inconsistent view of the file system. Okay. So, what echo does is the following: if P depends on a discarded W, because P depends on W, but it turned out that W was actually discarded. If that is the case, the various recovery modes they have, I will just give you some kind of idea. In practice, things can be much more complicated, but I am just giving you some simpler ones what they have come up with. Okay. In standard recovery mode, error on any further operation. Okay. So, basically what is happening is that there was the process issued a write, or it depended on the write somehow. Okay. So, P depended on write, and somehow it, because of a crash or whatever, it could not guarantee it. Okay. So, when it comes up, okay, you want to make sure that some recovery is happen, but at the same time there are other nodes on the system which could also be doing operation on the same on that particular thing which is on other parts of the system. Because notice that this particular file could be cached some other places. Okay. So, what you are planning to do is you are basically saying that anybody does any operations on those related files for which the write behind was dropped. Okay. You want to make sure it is an error. Ideal thing would be to send a signal to all the processes affected. So, but in the echo they actually just say that any further operation is an error. The reason why this is not a good solution is because this is immediate. As soon as this is notice happens, you are telling the process this has happened. Here it is only noticed when you actually do the next file system operation. So, it can happen much later. So, it is not such a good thing. Okay. In self recovery mode, the idea basically is that why constrain everybody. Okay. The only thing that we are worried about is open files, because open files only they might have lost something because somebody crashed somewhere. Okay. So, instead of saying that any operation is a problem on that set of directories or partitions of the file, okay, we will only bother about only those files which are open. Okay. And also they had some other model in mind. The model was that if there is a problem, if the application restarts, it will start using absolute path names again. Therefore, the restarted application should be able to proceed. The old process had some difficulty, fine, something was lost. But in the interest of availability, I will just assume that a new process started, and the new process typically at the beginning at least, before it gets the file handles etc., will be using absolute path names, and therefore it could be okay. But actually it turned out this fine distinction was not really used in practice, therefore it did not work out. Actually what you need is something slightly more subtle. What you need is something called a failure handle. That is, for each open operation, just like you get a file descriptor, you need another handle, what they call the failure handle. So, if a write or some operation no is issued with this handle, okay, that means that this and W arrow O, okay, then the basic idea is that this H also depends on W, okay. So, basically what are we saying? If there was a write that was issued with H, so first of all notice again one thing, you opened it in some time in the past. Now after some time you are doing a write and this write was issued with H, okay, or this another operation that was issued with H, okay. That means that there is a dependence between, if there is a dependence between W and O, we say that H is actually dependent on W, okay. So basically what we are saying is that anything that we are trying to mark all operations that are in somehow connected with what we should do in case there is a when that write is actually discarded, okay. If W is discarded, then any operation issued with H is going to be an error, because H is the thing that keeps track of what really happened, okay. And there is some subtle difference. There is one more thing they talk about, null recovery mode, which basically the problem with this was that all open files, it includes unfortunately the process P also, because when you have a current working directory and the process has a current working directory, so that file is, that directory is also open, okay. Now if you mark that also as inaccessible, then you have no place to stand, okay. That is causing a problem. Actually that is why you need to make sure that P's current working directory is not marked, okay. So there is some subtle differences between some of these modes, and so it turns out that if you really want to take care of application needs, there is a lot more things you have to do to handle the situation correctly. So we just looked at aspects relating to storage ordering. Again, let me just show a distributed file system where both the orderings are important, okay. This is a research file system that was developed at Berkeley about mid-90s, and you can see that if you have a lack of ordering, it can create some problems, okay. Either you can get a deadlock, or as we saw before, you can get inconsistency. So this is an example of how you can get a deadlock, okay. What is happening out here? There is a client here, client C, client B, and there is a manager. So manager you can assume as the party who gives access to exclusive access to files, okay. There are various parties trying to update certain things, and you go through a manager who keeps track of consistency requirements. So what is the first operation? You do a read. Let us say that this file actually is cached by B, okay. Now in this system they had the notion of something called forwarding read. That means that client C requests a read, this read is forwarded to B, but there is a problem in the network, whatever, it does not go immediately. That is why there is gap here. It takes some time, it is not instantaneous, it is taking time. In the meantime, before this forwarding read made it to client B, you get a situation where client has made a request for the write, okay. Now this manager, seeing that 3 has made a request for write, and it knows that somebody has got a thing, it does not know who it has got it, it could either be B or C, it generally sends a revoke to everybody other than the party who requested it. So sending a revoke to everybody, it goes to this, it goes to this. Of course 5, this revoke coming to C, it drops it because it knows it does not have it, it is a no for it. For 4, this 4 part, when it comes to B, it actually has to, it is valid for this, so it has to actually flush it through, it has to essentially take its dirty data and make sure it is flushed to disk. That is what B has to do. And let us say just after some time, B actually does a read, okay. Now it has to go through the manager again, because this is a distributed file, it has to get the tokens so that it can have access to it, because you are going to have what is called multiple readers can have a read lock, but only a single writer can have a write lock, okay. So that is why it is trying to get the read lock from here, okay. And so after 6, let us say that magically the same what I did here finally comes here. Now at this point the system is deadlocked. Okay. Why is it deadlocked? Client is waiting for the manager to do something about the write it is requested. Client C, right, what is it doing? It tried doing a read and it is try to do a read and it is waiting for B, right, because client C's read became a forward read, but that came, it is sitting in the queue much later than the other revokes, okay, and it is basically waiting for, client is waiting for the manager queue to give it the file, does not even have it, okay. Therefore, B is actually waiting for the manager, okay. C is waiting for B and the manager is waiting for C, okay, because why is the manager waiting for C? It's waiting for C because let me see, what is the reason why manager is waiting for C? Basically because C has initiated a read and you have to ensure that the revoke that has to be completed by client C, but there is some confusion because read might actually bring the file back here and it has to be revoked again, okay. So for this reason the operation read has to be completed by C, then only the state is becoming consistent across all the machines, okay. So because of this you can see that you need some kind of causal models, okay. For example, if you notice that client C is asking for a read and A is also requesting on the same file, then if you already issued the forward read, you can see the connection between forward read and this write, and you can essentially ensure that 3 is delayed and wait for this to be completed. You are doing this revokes, which is again broadcast. Again you have to ensure that these two things are delivered to client B and client C in a particular order. So, and there is, all these things happen causally, okay, that is why causal ordering is important here. In addition to all these things, you also have to ensure that there is effort type of ordering, otherwise you may get inconsistent operations, okay. Right now we are talking about read and write, but if you introduce things like directory operations, it could have similar things like what we discussed before, okay. So that is why distributed file systems are slightly difficult to engineer. There are a lot of ways in which things can go wrong, okay. And POSIX file systems, especially clustered POSIX file systems, are very difficult to engineer. So let me take one more example of another attempt of a distributed file system, okay, which also tries to do something interesting, okay. This episode distributed file system, it uses what is called redo undo logging. I will explain what this is soon, okay. And for efficiency it does some other interesting things. So we will just try to understand what is going on. This episode distributed file system, it uses write ahead logging, but because it is redo undo, in each node old and new value logging for every metadata update, it has an old and new value. In a read only logging, you do not keep the old values, okay, you only keep the new value in the log, okay. So because of this, because it is got redo undo, it is important that if buffer cache writes out any dirty data, it also has to be logged, okay. So it is going to be more expensive, okay, but it gives us some additional concurrency. So at some time in the future, the metadata updates make it to disk, and in case there is a crash, you check whether the transaction aborted. If the transaction aborted, then whatever metadata update that made it to disk, you have to unroll. and you can unroll because you have the old information. Whereas if the transaction committed, okay, then you look at the log and see which of those metadata updates actually made it to disk. If some of those things didn't make it to disk, you redo them. Okay. So in this model, even if there is it handles everything, you don't need FSK except for hard IO errors. That's the only reason why you need to do it, because the rest of it is being handled by this logic, transaction logic. Okay. So episode distributed file system, each local file system does redo undo logging, and this is in contrast to other file systems do redo only logging. Again, what is the difference? In redo only logging, you need to keep only the new value that is going to be the change value that has to go to the log. In the case of redo undo logging, you save both the old and new value so that you can roll back. In a redo only system, you can only go forward on a crash. Okay, you cannot think of coming back. So you have to be much more careful. I'll come to that soon. Okay. So typically it turns out you do what is called two-phase locking in redo only lock. Okay. Reason is that in redo only logging, you have to ensure that there is no read of uncommitted data. Okay. That means if you take a lock, you have to keep the lock till the transaction commits. So basically what you do is you keep on accumulating locks until commit, then only release it. Okay. So I made a mistake here. It should be redo only logging. This is not correct. It should be redo only logging. Okay. So there's another problem with two-phase locking, which is basically it's also difficult in layered systems. So two-phase locking is not advisable in redo undo logging, but it's required in redo only logging. Okay, basically because you can't have read of uncommitted data. There's another issue that this kind of file systems have to handle, how to handle cascading aborts. For example, suppose I have on machine A, okay, you have transaction 1 like this, and machine B you have transaction 2, the start of the transaction, end of the transaction, and you are updating A1, B1, okay, you're doing updates of some kind, and suppose there is some connection between this data and this data, okay. So basically in some sense this particular transaction has looked at this data, okay, modified versions, and then it completes the transaction, but before the transaction 1 commits, let's say this is a crash. So all this was sitting in temporary memory. In a sense, what has happened is that this is a subtransaction of 2 is a subtransaction of transaction 1. So in case this happens, you might have to go and undo this transaction. Okay. Luckily for you, if you are using redo undo logging, it's possible because you have the old information, you may be able to undo some part of it. Okay. So basically you have to keep the possibility that there can be cascading aborts, and only when the ancestor transaction is completed, then only you can release the data for the sub transactions. Okay. Otherwise, you will get a situation where, for example, B has changes for both transactional and transactional, but A doesn't have any time, because this essentially this is volatile and disappeared. So you have to handle this also. Okay. Now it turns out episode does not use two-phase locking, and because you don't have two-phase locking, you don't have to keep logs till end of transaction. You can drop, as long as you're done with it, you can drop it. And the reason why you can do it is because you have the undo operation. Even if the conflicting transactions come in, it is read something, okay, and somehow you are not able to proceed further, you can unroll it. So in a sense, each of the transactions can be unrolled. Therefore, even if because of some way the concurrent transactions have been ordered. If somebody reads some data which is uncommitted, you can always unroll it. Okay. So Episode actually what it does is, to handle both these problems, it does something called, takes all the active transactions, it computes an equivalence class of those transactions that modify the same object, and all transactions of this class either commit together or not. Okay. And so this is some kind of an optimization on top of what normal transaction models. And the basic reason why they have to do this kind of things is because you want to let each of those local file systems flush their things to disk instead of a coordinated two-phase model. Okay. So each particular local file system can flush things to its disk, and only on failure do we have to figure out what to do with it. And if the failures are much less than normal operation, then you are certainly going to win. Whereas in the case of redo only logging, you have to wait till whole commit has taken place. So it can be problematic. Again, in a sense, what is happening is that just like the difference between a file system and database, the file system typically has much shorter transactions, whereas databases can have very long running transactions, because that's determined by the application, not determined by the kernel. So the file system typically does small things. Okay, basically it handles only storage related operations. Therefore, typically its operations are small, whereas the database transactions, they involve application level data, and they can be arbitrarily stretched out. So for that reason, for having concurrency, you need to ensure that multiple transactions can be in place at the same time, and you decide how they are going to be flushed. There is a conflict, you roll back. Now, distributed file systems also are coming closer to the database model, because they are doing across a network, and therefore they can take longer time than a typical local file system operation. And therefore, you also need to possibly do something better than redo only logging. If you do read only logging, then your parallelism is seriously constrained, whereas if you do redo undo logging, then all the updates of the metadata can go in parallel across all the nodes without having to wait for the commit to complete, and only on failure situations do you have to do something serious. Okay. So that's what basically we're saying. There's some advantage of redo. If you do redo undo logging, it is better than redo only logging, basically because uncommitted data read also is possible, and because there is no undo capability in read only, update home disk locations cannot occur till transaction commits. Okay, the concurrency is reduced. It even constrains the buffer cache on when to write. Okay, so this makes it for a slightly slower, less concurrency. But the problem with this is also that you have to save both the old data and the new data. That means what you have to log also becomes higher. Okay, so you are sending more stuff. Okay, and you have slightly more complicated algorithm out here. Okay, so I think I'd like to conclude today by summarizing what we have looked at so far. So basically, there are a lot of orderings in a distributed file system. If you look at NFS, it was very cavalier in terms of what it decided, because it basically had a very simple model. All it did was, it just said, I cache something, every so often I discard my cache. Okay, and if it so happens that in that intervening period somebody else has done some other operation somewhere else, I am not going to be consistent. Okay, that is what basically. So whereas if you look at the more elaborate distributed file systems, they attempt to handle things better. And I talked about echo file system, which had a fairly well thought out model, and we also looked at echo file system, episode file system, which also tries to give some guarantees, but it is done through transactional models. Okay. So, the interesting thing about for us is that there are varieties of orderings that are there in a system like distributed file system. It can happen at the device level, at the message level, application level. When I mean application, I also mean kernel level, okay, because your file system is sitting on top of a messaging system. So, the distributed file system is actually sitting on top of this messaging system, okay. On top of the file system, there could be another application sitting on top of it, okay. So, there are various orderings going on at each of these levels. So, you can do like what has been done in other areas, what is called cross-layer optimization. It is in principle possible to come with an ordering framework across all these layers, but it has proved to be very difficult and nobody has seriously attempted it, okay, because it is quite tricky, okay. For reasons of availability and reliability and consistency, it is not something trivial. So, basically people have tried to avoid getting into cross-layer optimizations here, okay. But I think someday in the future probably some of this will happen, especially with storage class memories. I think it might happen, okay. So, with this I am going to conclude today's talk, today's lecture.